Come on, class, be quiet. We have lots to do today, okay? No recess unless you're quiet. Jimmy, put your pencil out of your mouth, okay? You need that to write. Hello? Damn it, right now? Okay, I'm on my way. Sorry, kids. It's time to rock and roll. I came as fast as I could.
Ah, yes, my favorite agent. Take a seat.
Yes, President. At your service.
I need you to execute Mission 407 again.
Mission 407 again? Last time the whole mission was compromised. All our communication devices were tapped.
I know, don't worry. I have my team cook up a secure chatting system. I'll let them show you how it works.
I guess this is my Q. Name's Q.
My head engineer Q, tell my favorite agent about SecureChat.
SecureChat is a hardware-backed secure messaging service. It's specifically made to transfer information with high security across the world. Our implementation follows the 3 pillars of encryption: what you are, what you have, and what you know. You'll each just need a phone and these 2 physical devices.
Devices? I love a new gadget. Well, I already have my phone. What else do I need?
The devices you need are right here.
Good golly, what are those and how do we use them?
You each need to have a shared set of encryption keys in this USB to communicate securely over a channel. Then you will use these switches to index which key you and the Madam President want to use. Now let's start the exchange of keys. Press this initialization button and then we can start. You can see the progress of the key exchange on the LEDs. The values you see on the displays are just a small portion of the long keys we are creating. We display them here so you know the system is working. When it's complete, all the LEDs will flash to indicate that the key generation has completed. I have my remote engineer Owen here and he's going to explain you what's happening under the hood.
Sure thing, guys. Let me explain. So what does it mean to initialize a SecureChat hardware? Well, our security is based upon the setup of 2 major components, the hardware state and the user state. The hardware state has components such as an AES key store and the FPGA lookup table embedded in the hardware. There's also this hardware key that is unique to each pair of users. It's not user initialization, but it's good to keep in mind. While the hardware is setting up, the users will need to agree on what is to be a secret key schedule. I'll explain what that is in the next slide. This entire setup must happen in person to securely do these initializations over Bluetooth. For the hardware, we do 2 major things. One thing is we use the FPGA logic to generate a random hardware lookup table. This table is implemented specifically in hardware for security reasons. You'll see later on that keeping these entries as far away from the software is definitely good for our security pipeline. The other thing we do is use the Diffie-Hellman algorithm to securely generate a large store of AES keys. The Diffie-Hellman algorithm is specifically designed to send encryption keys over insecure channels, and we use it to generate many, many keys to form our key store. Also, you will see later why having many keys is a benefit for us. It gives us security complexity where an attacker will have difficulty choosing the right key at the right time. After this initialization, we will find that the lookup table and the key stores will be symmetric on both users of our devices. So what is the user state initialization? Now, the users are going to, during the meeting, they're going to agree on a secret password schedule. And this is going to be a physical pattern of switches that they choose. Now, this can be a varying complexity. This can be something that changes every day, every hour, or depending on the needs of the user, it can be something very complicated, such that it's difficult for someone to obtain this password. So why do we need all this setup? For one thing, you can imagine, without understanding our pipeline yet, that the hardware might be compromised. That if someone has your device, they can message. The thing is, someone will need your switch password specifically. Even if they have your hardware, they will need the right code at the right time. On the same story, if they have your code, the person will need your device, and your device will have to be initialized such that it has the correct FPGA hardware table and the correct set of AES key stores. In the worst possible case where everything is compromised, this is fine too. Because for us, this initialization does not just happen once. It's actually a good practice to do this many, many times and often, such that your hardware is constantly in a random state and you always have fresh passwords.
Thanks, Owen. But how do I actually use the app?
Oh, and why don't you hop in a call with Bryson and show our agent how it works?
Sounds good, boss. I'm ready on my end, Owen. Let's show them the setup.
Take a look at my setup here. You can see I have my phone here loaded on Android app. We have the OFS board connected to the D1, and the D1 is currently running Linux. I'd like to point out that I have a USB stick here plugged into the D1, and it currently has a copy of an AES key store. At this point, Bryson and I have both completed our initialization setup and have identical hardware lookup tables and symmetric AES lookup tables. One other thing to say, if you look at my other screen here, you should be able to see a debug output of our D1 app. So when we do our decryption and encryption, you should be able to see exactly what the D1 is doing here. I'm going to get us started here by authenticating into the app here. You can see request my fingerprint. Now that I've authenticated, I will hand it off to Bryson.
All right, fantastic. Thanks, Owen. So as you guys can see, I have all of the same components on my end, so we're ready to go. I've already authenticated with the app, and now I'm in. But as you can see, my phone does not have a serial connection via Bluetooth to our encryption device, so it cannot communicate. So we're going to change that by going to the Bluetooth page, and we're going to start listening for discoverable Bluetooth devices around us. We can see we found HC05, which is the Bluetooth module that we want to connect to. So I'm going to click on it, and it's going to attempt to connect to that device. It's asking for my pairing key, 1, 2, 3, 4, 5, 1, 2, 3, 4. And as you can see, I've successfully connected to the device. So now we can begin our communication.
Okay, great. Now, if you notice on my phone here, you'll see that I have already paired. So before we started, I ensured that my phone is already connected to the device. Now, the first step of our process is for Bryson and I to enter the same channel. Bryson, why don't you go into channel CPAN 391?
Fantastic, I'll do that. Now, it's all right that any malicious onlookers would know our channel name, because everything that goes to this channel is going to be heavily encrypted. So this actually doesn't have to be a secret. All right, I'm in the channel.
All right, great. So now that Bryson and I are on the same channel, we're ready to send our encrypted messages. Now, very important step beforehand. We need to ensure that we both have the exact same secret key switch pattern. So Bryson and I have already discussed beforehand, and we have identical switch patterns already. Bryson, are you ready?
I'm ready, Owen.
Okay, so if all that worked out, I'm going to send our first encrypted message. I'm going to send this message here. Now, on the phone, you can see that I've successfully sent the message. And on the Linux debug output, we have done the full encryption decryption pipeline. Bryson, did you get the message?
Yeah, exactly. On my side, you can see the exact same thing. I've successfully decrypted hello Bryson, and I'm going to send a response. Hello, Owen.
Fantastic. As you can see here, I successfully received these messages. Now, what we're going to do next is show you that the switches are actually choosing the encryption key we're using for this. So Bryson is going to go ahead and choose a different key schedule, and I'm going to stay on the same one.
All right, I'm going to put my key combination to our next iteration combination.
Great. So now that we are on different key patterns, Bryson's going to go ahead and send me a new message.
All right, I'm going to send a message to Owen. There it's sent. And the word is secret.
So if you take a look at my phone screen here, you can see that I have successfully received Bryson's message. However, this time it's garbled mess. And this is exactly because I do not have the correct secret key pattern. So now I'm going to switch my keys, my D1 switches, to the correct key pattern, and Bryson's going to run the message again.
All right, you ready for the message, Owen?
I'm ready, Bryson.
All right, I'm just going to send the message, and we'll see if it's successful this time.
Take a look. So I've received another message, and this time it is perfectly decrypted. This time it was the same message as last time, but because I used the correct AES keys, Bryson and I are able to have secure encrypted messaging.
Wow, thanks for that demo, Owen and Bryson. Your app looks secure and nifty. Can you tell me more about how that Bluetooth stuff works?
Of course I can. Let's talk about how your device communicates with your phone to provide its encryption and decryption services. Your hardware device and mobile phone communicate over a serial socket that implements the RF-COM Bluetooth protocol. Embedded on the device is an HC05 Bluetooth module, which is configured to be in slave mode, waiting for a phone to discover it and control it. This configuration is performed in C code, executed on the D1 SoC, which sends these AT commands to the Bluetooth module to make it discoverable. Each unique AT command manipulates the state of the Bluetooth module to prepare it for pairing. On your phone, the Java code on the app uses a Bluetooth library to discover the HC05 device, request a pair, and set up serial Bluetooth sockets to communicate. With your phone paired to your device, you can now chat securely. Good luck on your mission.
Thank you, Bryson.
Yeah, thanks. That was dandy. Okay, so does that mean we have to be together every time we want to use the app?
Oh, you silly agent. Our backend expert Rahul can tell you how it works. Rahul, why don't you hop on?
Firstly, I want to talk about channels, which are the backbone of our communication protocol. When sending messages, your encrypted messages will be broadcasted to a dynamic communication channel that you and the president will decide to listen to. This aspect of the device is inspired by encrypted radio communication. To further explain the workflow, when you send a message, it is firstly encrypted by your device, then it is sent to the backend using Socket.io or by the app. The backend is a Node.js server on an AWS virtual machine with no databases, which sets up the communication channels and sends the messages to the subscribers on the channel, from where the recipient uses their device to decrypt and receive the messages.
Thanks for that explanation, Rahul. At this point, maybe you need a summary of how the encryption pipeline works.
Yeah, that'd be great.
All right, I'll let my twin brother take the lead on this one.
Hello, twin brother. It's so nice to see you here. Now, I'll show you a schematic of what exactly is happening when you try to send a message from Madam President's phone to the Agent Dana's phone. After they agree upon this key switch pattern, they input this to generate an input index to be used as a key from a randomizer lookup table that we created. And the output index is going to be later used for fetching an AES key from the flash drive. This is going to be our first AES key. And the second one, as we know, is coming from the hardware. It's encoded in that. And then having these two keys, we start the encryption process as soon as we send this clear text, hello, Agent Dana, from the president's phone. We first encrypted using the hardware encryption key, the level 1 encryption. And then as you can see, we have this gibberish text here. Then we use the key from the flash drive and encrypt it again to have this new gibberish text. And our 2-layered encryption is completed at this point. And then it's passed to the channeling system to send it to Dana. And if I just scroll down here, you can see Dana's phone has the exact same schematic, the same set of switches that go into the randomizer, output an index, gets the same AES key from the flash drive, and we already have the same AES key encoded in the hardware. So again, we have these two keys to be used for decrypting this message. And after the first decryption, we still have the gibberish. Then the second layer of decryption with the hardware key, we finally receive the clear text, hello, Agent Dana, on Agent Dana's phone.
Oh, that's great. So it doesn't matter if my device gets stolen or a switch pattern is somehow compromised. They would need my device and the information I know and my fingerprint to break into our messages. Oh, that's absolutely brilliant.
Well, I hope you understand it well, because you have to go right now. There's a car waiting for you out front.
Alrighty, President. I'll chat with you soon. Thanks, sir. You've been of great help to us.
Anytime. Now run, kid. You got our missions complete.
But wait, which channel name do you want to chat on?
Use channel name Martini.
Got it. Time to rock and roll.